All right, let's dive into something you might think you already know.
Yeah.
But trust me, there's a twist to this one.
Okay.
Today, we're going deep on those numbers that don't fit into perfect squares.
Right.
We're talking the non-squares.
Okay.
And for this deep dive, we're going to the online Encyclopedia of Integer Sequences.
Okay.
That's OEIS.
Got it.
It's entry A000007 if you want to look it up.
Oh.
What's fascinating is how much depth this sequence has.
Yeah.
I mean, we're always looking at those elegant squares.
Right.
But what about the numbers that just don't fit that mold?
Yeah, the ones that resist the perfect form.
Exactly. There's a whole universe of mathematical connections here.
Absolutely.
In this simple concept.
That's true.
So I'm looking at the initial terms here. 2, 3, 5, 6, 7, 8, 10.
Yeah.
It's like all the leftovers after we take out the squares.
Right.
But the OEIS gives this formula. AN, N plus floor, 12 plus quart N.
Okay.
I mean, is that just a fancy way to say not a square, or is there more?
Oh, there's definitely more to it.
Okay, good.
That formula, it's not just identifying them, it's actually generating them in a specific order.
Right.
That floor function, it's doing the heavy lifting. It rounds down to the nearest whole number.
Interesting.
It's like a mathematical sieve.
Okay.
It filters out all the squares and leaves us with this really precise sequence.
That's pretty neat, seeing the formula capture that idea.
It is cool.
Okay, but the OEIS also mentions divisors.
Right.
Right. Something about the number of divisors being different.
Exactly.
For squares versus non-squares.
Yeah, and this difference actually reveals a very fundamental distinction between them. Non-squares, they always have an even number of divisors.
Okay.
While squares have an odd number.
I don't know if I'm seeing that right away.
Okay, sure.
Can you give us an example to make that a little clearer?
Oh, absolutely. Let's take the number 12.
Okay.
It's a non-square, right?
Right.
Its divisors are 1, 2, 3, 4, 6, and 12.
Okay.
6 divisors.
6, so an even number.
Yeah. Now compare that to 9, which is 3 squared.
Right.
Its divisors are 1, 3, and 9.
Okay, so only 3.
Exactly, an odd number.
Okay, I'm starting to see it now.
Yeah.
There's a symmetry with the divisors of 12. But with 9, that middle divisor, the 3, it doesn't have a pair.
Yeah.
Is that because when you square a number, you're basically like duplicating a factor?
Exactly. That duplication when you're squaring leads to that single unpaired divisor right in the middle.
Yeah.
So that makes the total number of divisors odd. But non-squares, they don't have that duplication. So they always maintain those paired up divisors. So even number.
This is really making me look at these basic numbers differently.
I know, right?
And get this, the OEIS entry even mentions Theaetetus of Athens.
Oh, wow.
Who was proving things about these non-squares way back in the 4th century BC. He was focused on the irrationality of their square roots.
Okay.
So what exactly did he prove?
He demonstrated that the square roots of these non-square numbers can't be expressed as just simple fractions.
Interesting.
Like, for example, the square root of 2.
Yeah.
You can't write that as a neat ratio of 2 whole numbers. This concept of irrationality, it really challenged how people understood numbers back then.
So he wasn't just playing around with non-squares.
No.
He was wrestling with like a fundamental concept about the nature of numbers.
Exactly. A big concept.
It's quite a legacy.
It is.
For something that seems so straightforward at first.
Totally.
It highlights that even exploring simple mathematical concepts can lead to really profound insights.
That's true.
And even philosophical questions.
Absolutely.
His work with non-squares really impacted how mathematical thought developed.
For sure.
Wow, that's putting it into perspective.
Yeah.
Okay, before we get too philosophical, there's one more thing in the OEIS entry.
What's that?
That caught my eye, something about consecutive non-squares.
Okay.
And their averages.
Right.
What's the deal with that?
Well, it shows another fascinating pattern.
Okay.
If you take 2 consecutive non-squares of the same parity, meaning both even or both odd, their average is directly related to a perfect square.
Oh, hold on. That sounds kind of complex.
Yeah, it's a little tricky.
Can you give us an example to break that down for the listener?
Let's consider 6 and 8.
Okay.
They're both even, right?
Yeah.
And they're consecutive non-squares. Their average is 7, which itself isn't a square.
Okay.
But if we take the average of 7 and 8, we get 7.5.
Okay.
And what's interesting is that the square root of 7.5 is approximately 2.74, which when squared gets us really close to 7.5.
Okay, so it's not that the average is a perfect square itself,
right,
but it's tied to the square of a decimal number.
Exactly.
There's a hidden connection there. Even if it's not immediately obvious.
It's subtle.
It's like a mathematical echo of a square.
I like that.
This kind of subtle pattern is what mathematicians are always on the lookout for, right?
Yes, absolutely.
Within these number sequences, it points to deeper mathematical truth.
For sure.
That we might miss.
It's true.
This is reminding me of what you said earlier.
What's that?
About how exploring one sequence can open doors to a whole network of ideas.
Oh, yeah.
What else does this non-square sequence connect to?
Wow.
The OEIS mentions discriminants of indefinite binary quadratic forms.
Right.
I don't even know what those are.
Yeah.
And it links to other sequences like A00007969 and A00007970. Is this where things get really wild?
This is where it gets wonderfully interconnected. Discriminants of indefinite binary quadratic forms.
Yeah.
Sounds intimidating, I know.
Right.
But it actually links our non-squares to the field of number theory. Yeah. And those other sequences you mentioned, they're not just random numbers. They're pieces of a bigger puzzle, each with their own patterns and connections.
It seems like we've just scratched the surface here.
We have. It's a vast mathematical landscape.
This is mind-blowing.
I know, right?
We started with a simple idea, numbers that aren't squares.
Yeah.
And now we're talking ancient Greek proofs. Hidden patterns in averaging and connections to other areas of math.
That's amazing.
It's like we've opened a door to a secret world of numbers.
Totally.
That's the beauty of mathematical exploration. You never know where a simple concept might lead.
It's true.
And we're just getting started.
We are.
Stay with us as we unpack the world of non-squares in part 2.
That'll be fun. Welcome back to our deep dive into the non-squares.
You know, we've seen how these numbers that we often overlook connect to some really big ideas in math.
Absolutely.
I have to admit, though, all these connections are fascinating. But part of me is wondering, like, why should anyone really care about this?
Right.
Do non-squares actually matter in the real world?
That's a great question.
Yeah.
It is a crucial question to ask sometimes, you know?
Yeah.
We get so caught up in the beauty of this abstract math that we forget to connect it back to our everyday lives.
Right, exactly.
But rest assured, non-squares do have practical applications.
Okay, now I'm intrigued.
Yeah.
Where do these non-squares show up?
Oh, where?
Outside of pure mathematics.
Think about computer science.
Okay.
Non-squares, they pop up in algorithms that deal with generating prime numbers.
And those are essential for...
Those are essential for cryptography.
Right.
And secure online transactions.
Wow, okay.
Yeah, you wouldn't believe how much our digital world relies on these rebellious numbers.
So non-squares are keeping our online shopping sprees safe.
They are.
That's pretty impressive.
I know, right?
Where else do they make a difference?
Well, they even play a role in physics. Calculations related to things like wave propagation and energy levels sometimes involve non-squares.
Really?
It's like they're woven into the fabric of the universe.
Wow.
They influence how things move and behave.
I never would have imagined that.
I know, right?
These leftover numbers?
Yeah.
That's such wide application.
That's pretty cool.
It's like a hidden code running through different areas of science.
It is. It reinforces that interconnectedness that we keep seeing in math.
Yeah.
You know, exploring one concept often leads to these unexpected applications in other fields.
It's true.
Non-squares, they may not be as famous as, let's say, Fibonacci numbers.
Okay.
But they're essential players in the grand scheme of things.
This is making me think about all those times in math class when I was like, when am I ever going to use this?
Right.
Maybe the answer wasn't about a specific formula, but about like developing a way of thinking that helps us see patterns and connections.
It's a great point.
So studying math, even something like non-squares, helps us develop a more analytical mind.
It does.
And a problem-solving mindset.
It's about training our brains to recognize these patterns.
Okay.
Connect different ideas and think critically.
So understanding non-squares can make us better thinkers.
It can.
That's a pretty good reason to care.
I think so.
But we also talk about how exploring one sequence can open doors to other mathematical ideas.
Yeah.
Where could our listener go from here?
Oh, there are so many paths to explore.
Okay.
You know, the connection to irrational numbers could lead someone down a fascinating rabbit hole.
Okay.
Delving into different types of numbers and their properties.
So this deep dive isn't just about learning facts about non-squares.
No, not at all.
It's about sparking curiosity and giving our listener a starting point.
Yeah, like a jumping off point.
For their own math journey.
Exactly. We've provided the map.
Okay.
Now it's up to them to choose their own adventure.
I like that.
They might delve into number theory.
Right.
Exploring those discriminants of indefinite binary quadratic forms.
Yeah, we did mention those.
We did.
Maybe they'll get lost in the OEIS.
Right.
Uncovering those hidden connections between sequences like A00003969 and A00007970.
Okay.
It's like we've given them a key to a secret library.
It is.
Filled with endless mathematical treasures.
And the best part is, there are always new treasures to be found.
Right.
That's the beauty of math.
Yeah.
It never ends.
Before we wrap up this part, let's do a quick recap.
All right.
What are the key things to remember?
Okay, so first and foremost, a non-square is any whole number that can't be formed by squaring another whole number.
Okay.
Sounds simple.
Right.
But as we've seen, it leads to some pretty complex ideas.
Definitely.
And they should remember that formula for generating the nth term of the sequence.
It's a great example of how math can capture a simple idea in a really precise way.
Absolutely.
And they should remember that even though non-squares don't form neat squares, they have their own special properties.
Yeah, like always having an even number of divisors.
Oh, and definitely remember Theaetetus of Athens.
Oh, yes.
And his work on irrationality.
Yeah.
It's a reminder that people have been thinking about these ideas for centuries.
It is.
And that even basic concepts can have big implications.
It's true.
And finally, they should remember that non-squares are far from insignificant.
Right.
They pop up in all sorts of fields.
In computer science, physics, and they offer a gateway to so many other math ideas.
So even though we're at the end of this part of our deep dive, the exploration doesn't have to stop.
No.
In our final part.
Okay.
We'll leave our listener with some questions and ideas for further exploration.
So good.
Stay tuned. Welcome back to the final part of our non-squares journey. We've uncovered hidden patterns, historical connections, and even real-world applications.
Yeah, it's been quite a journey.
But now I'm wondering, is there a way to actually see these non-squares?
See them?
Yeah, I mean, we've been talking about them in terms of numbers and formulas, but can we visualize this concept?
Oh, that's a great question.
Yeah.
One that really makes us think outside of those abstract symbols.
Right, exactly.
Can we actually represent something that's defined by what it's not?
Yeah, it's a challenge.
It is, for sure.
I keep picturing squares as those neat little grids, you know?
Yeah.
But how do you actually visualize their absence?
Right.
It's almost like trying to draw a picture of silence.
I love that analogy. It really captures the challenge.
Yeah.
Maybe instead of focusing on the absence itself, we could shift our focus to those properties we've talked about.
Like what?
Well, like how non-squares always have an even number of divisors.
Right. Okay.
You know, a sort of balance or symmetry. Could we maybe express that visually somehow?
Interesting. So instead of the squares themselves, maybe we look at those gaps between them on a number line.
Exactly.
Those gaps would represent the non-squares.
Right.
And maybe there's a visual pattern to those gaps.
Precisely. It's like we're translating this mathematical concept into a different language, you know, a visual one.
And mathematicians do this all the time, right?
They do. They're always finding new ways to represent and manipulate ideas.
This is making me think about math totally differently. It's not just about, you know, crunching numbers.
Yeah.
It's about creativity and finding different ways to express concepts.
Absolutely. And who knows, maybe someone listening right now will be inspired to create their own visual representation of non-squares.
That's a great idea. We'd love to see what you come up with.
Definitely.
But before we go, let's zoom out to the big picture. What's the lasting impression we want to leave about these not-so-square numbers?
I hope our listeners realize that even the simplest mathematical concepts can have such surprising depth.
Yeah.
And that they connect to this vast network of ideas.
And that math is so much more than memorizing formulas.
Absolutely.
It's about curiosity and exploration and seeing the world in new ways.
Perfectly said.
It's amazing to think that a deep dive into non-squares could lead to so many fascinating discoveries.
I know, right?
It just shows that there's always something new to learn, even in the things we think we already know.
That's the beauty of it.
Thanks for joining us on this mathematical adventure.
It's been a pleasure.
Until next time, keep exploring, keep questioning, and keep diving deep.